Assalamu alaikum. Welcome to the second part of the series on how to implement fuzzy logic control in MATLAB Simulink software. Friends, today I am going to teach you the following topics. Number 1. Basic introduction of the fuzzy logic control. Number 2. Mamdani fuzzy inference system. Number 3. Takagi sugeno fuzzy inference system. Now let's start about the basics of the fuzzy logic control. As already discussed, fuzzy logic approach is presented by Lutfi Asghar Zedha in 1965. Each system always have input and output variables to control its response. Fuzzy logic basically deals with the process of dealing with these inputs and outputs variables. The basic process of fuzzy logic controller consists of mainly three steps known as fuzzification, rule-based inference engine, and defuzzification. At the first stage, the input and output of the system is need to be clearly defined. Let's consider an example of load frequency control of power system. Consider the figure which shows the transfer function model of the power system. We know that commonly governor is used to control the speed of the turbine in order to keep the frequency of the system constant. Whenever load is suddenly increased, the power system frequency is decreased. Governor senses this decrease in speed and sends the signal to turbine to open its valve in order to increase the power generation. When generated power and increased load demands are equal, the system frequency comes to a stable value of 50 or 60 Hz. It means that change in frequency is the input and the turbine valve position is the output in this case. Friends, now we have clearly defined the input and output variables for this case. Now we have to define the range of these input and output variables in the form of various membership functions. This is necessary to provide the different rules for different load variation. To know the minimum and maximum range of the input, let's consider the formula. We know that change in frequency is equal to reference frequency minus measured frequency. Reference frequency is always 50 or 60 Hz. And measured frequency is obtained at the every instant of time. Let's consider the case of load increment. When generation and load demand are equal, then system frequency will be stable at 50 Hz. Therefore, change in frequency in the normal state is 0. Now suppose due to increase in load, system measured frequency reduces to 49.9 Hz. Then change in frequency will become 0.1 Hz. Similarly, if we consider the huge increase in load demand, then system frequency may reduce to very low value resulting in difference of 2 Hz or even more, due to which the system frequency will suffer from undershoot as shown in the figure. Similarly, consider the case of load decrement. Suppose due to sudden decrease in load, system measured frequency increases to 50.1 Hz. Then change in frequency will become minus 0.1 Hz. Similarly, if we consider the huge decrease in load demand, then system frequency may increase to very high value resulting in the difference of minus 2 Hz or even more, due to which the system frequency will suffer from an overshoot as shown in the figure. Based upon these increment and decrement in load values, we observe that system frequency may change from minus 2 Hz to plus 2 Hz or even more in some cases. It means that minimum and maximum input range for change in frequency is between minus 2 to plus 2 or little bit higher for safety purpose. Now we have to divide this input range into different membership functions in order to become able to assign different rules for different input values. Based upon this, change in frequency input range with its membership function is shown in this figure. It may be noted that input change in frequency has 5 membership functions, namely HO stands for high overshoot, LO stands for low overshoot, NF stands for normal frequency, LU stands for low undershoot, and HU stands for high undershoot. Friends, these 5 membership functions are made arbitrary. You may increase or decrease the number of membership functions depending upon the situation. Higher number of membership function will increase the accuracy, whereas it will also increase the complexity of the system. Furthermore, the names of these membership functions are also assigned arbitrary for easy understanding. You may assign any name for your convenience. Moreover, it may be noted that we have taken triangular membership functions here. Friends, fuzzy logic control has the variety that you may choose various types of membership functions depending upon the type of the system, such as triangular membership functions, trapezoidal membership functions, Gaussian membership functions, and many more. However, among these membership functions, triangular and trapezoidal membership functions are most commonly used. At this stage, we have defined the input ranges with its membership functions. Now we have to define the range of the output variable. As our output variable is turbine valve position, therefore its range may consist from 0 to 1, where 0 means fully closed and 1 means fully opened. Now we have to divide this output range into different membership functions in order to become able to assign different rules for the different values. Based upon this, turbine valve position output range with its membership functions is shown in this figure. It may be noted that turbine valve position has 5 membership functions, namely FC stands for full kilos, HC stands for half kilos, NO stands for normal open, HO stands for half open, and FO stands for full open. These 5 membership functions and their names are made arbitrary for easy understanding. Friends, at this stage we have clearly defined the input and output with their names, ranges, and membership functions. Let's now start the process of fuzzy logic control. Look at the figure. It shows the basic process of fuzzy logic control. The first step is fuzzification. Fuzzification is the process of converting the crisp input to a linguistic variable using the membership function stored in the fuzzy knowledge base. Or in other words, it is the process of making a crisp quantity into a fuzzy quantity. For better understanding this crisp number and fuzzy quantity, let's consider the same example of load increment case. Suppose due to increase in load, system frequency reduces to 49 Hz, resulting in difference of 1 Hz. Now this 1 Hz is a real number or crisp number. Now to convert this crisp number into fuzzy linguistic variable or number, we have to see in which membership function this number lies. By looking at the figure, it may be observed that 1 Hz lies in the membership function of LU, namely low undershoot. It means that this low undershoot is the fuzzy linguistic variable. Now we need to determine its membership degree. You can see on the vertical axis membership degree is written. To determine the membership degree of 1 Hz using the graphical method, you can see it has the membership degree of 1. It means that now this 1 is the fuzzified value. This membership degree may vary with respect to the crisp number. Suppose this value is 0.8 Hz, then its membership degree by using the graphical method is 0.8. It may be noted that in the real calculation, mathematical expressions are used to calculate this membership degree. Friends, at this stage, the first step of fuzzy logic control process known as fuzzification is completed. Now the second step is rule-based inference engine or fuzzy associative memory. In this step, fuzzy logic uses if-then type fuzzy rules to convert the fuzzy input to the fuzzy output, as shown in the figure. This stage is used to assign the decision or control actions rule based upon the input values. In other words, it is a fuzzy truth table which shows all possible outputs for all possible inputs, and it is easy to create. Let's consider the same example of load frequency control. We have to assign the rules to fuzzy logic controller. Just think carefully. When load is increased, frequency is decreased. Now what we have to do? Can you imagine? What should be our signal? Whether to open the turbine valve or close the turbine valve? The correct answer is we have to send the signal to open the turbine valve in order to increase the generation. Therefore, now the rule will become as below. If change in frequency is positive, then open the turbine valve. Similarly, for load decrement case, the rule will become if change in frequency is negative, then close the turbine valve. By this way, all the rules are assigned carefully to the fuzzy logic control. If there are many rules activated at a time, then their aggregation is carried out to obtain the single output. Consider the figure in which 3 rules are activated at a time. As we need the single output to take the control action, therefore in this situation aggregation of the rules is carried out in order to obtain the single output. Consider another example of person height. Suppose if a person has a height of 6 feet and 2 inches, then what will be his category among very short, short, average, tall and very tall? From the figure it is noticed that he is 75% in tall category and 25% in very tall category. Therefore, we need to aggregate all these rules to obtain the single output. This aggregation basically combines all fuzzy conclusions obtained by the inference into a single conclusion. This aggregation is carried out by fuzzy operators. A simple max-min method of selection is used where the maximum fuzzy value of the inference is used as the final conclusion. Most common fuzzy operators are used as AND operator and OR operator. In the AND operator, minimum of the all values is taken, whereas in the OR operator, maximum of the all values is taken, as shown in the figures. Now the last step is defuzzification. Defuzzification is the process of converting the fuzzy value obtained from the composition into a crisp value. Or defuzzification is the conversion of a fuzzy quantity to a precise quantity, just as fuzzification is the conversion of precise quantity to a fuzzy quantity. This defuzzification is necessary since controllers of the physical system requires discrete signals. Consider the example of load frequency control again. We have the rule if change in frequency is positive, then open turbine valve. Or more specifically, if change in frequency is HU, then FO turbine valve. Means fully open the turbine valve. Now how to make fuzzy logic controller understand about this full open? Because full open is a name, not a number. Therefore we have to defuzzify this name into a crisp number. By using the graphical method, it can be seen that full open in this case means open the turbine valve up to 0.9 or 90%. However, it may be noted in real calculation mathematical expressions are used. Therefore, it means that defuzzification strategy is aimed at producing a non-fuzzy controlled action, or we can say defuzzification means the conversion of the fuzzy output values into crisp values. For this purpose, different mathematical methods are used for defuzzification. Some commonly used defuzzification methods are center of gravity or centroid method, weighted average method, or mean of maximum method. The center of gravity method finds the point where a vertical line would slice the aggregate set into two equal masses. Mathematically, the center of gravity can be expressed as below, where mu is the membership degree and x is its value. In other words, all these values with their weights or membership degrees are taken into account to find the center of gravity or single output. A reasonable estimate can also be obtained by calculating it over a sample of points. Consider the figure which shows the output values with their membership degrees. Suppose we have to find a single defuzzified output for this figure using the center of gravity method. To do this, just take all the values, multiply them with their membership degrees and divide them with their membership degrees as shown here. It may be noted that here 0.1 is written 3 times because 0, 10 and 20 are 3 values which all have the membership degree of 0.1. That's why it is used 3 times. Now the single defuzzified output obtained by using center of gravity method is 67.4. It means that fuzzy logic controller has to take action based upon this value. Another method for defuzzification is weighted average method. In weighted average method, only the core values with their membership degrees are taken into account, divided by the sum of their membership degrees. Just look at the figure. In this figure, we are considering only 2 values, A and B, rather than taking all samples. Therefore, its weighted average is equal to A multiplied with its membership degree 0.5 and B multiplied with its membership degree 0.9 and divided by the sum of their membership degrees. It means weighted average method is formed by weighting each functions in the output by its respective maximum membership value. It produces results very close to centroid method. Furthermore, it takes lesser computational time. Another method for defuzzification is mean of the maximum method. In this method, mean of the 2 maximum values is taken. Just look at the figure. You can see from the whole figure only 2 maximum values are taken and its mean is calculated to obtain the defuzzified output. Friends, at this stage we have successfully discussed the whole process of fuzzy logic controller. Friends, fuzzy logic controller has basically 2 main types, namely Mamdani fuzzy inference system and Takagi sugeno fuzzy inference system. Now I am going to discuss the Mamdani fuzzy inference system. Friends, the basic difference between Mamdani and Takagi sugeno fuzzy inference system lies in their defuzzification method. Rest of the procedure and steps are same for both the system. The Mamdani method is most commonly used method in fuzzy logic control. The Mamdani method was introduced in 1975 by Professor Ibrahim Mamdani of London University, who built one of the first fuzzy systems to control a steam engine and boiler combination. He applied a set of fuzzy rules applied by experienced human operators. Just look at the figure which shows the basic steps of Mamdani fuzzy inference system. You may be surprised to see that it is the same figure which we have already discussed. Yes, you are right. In fact, the Mamdani fuzzy inference system is same as we have already discussed about the basic fuzzy logic process so far. However, I am discussing it again to clarify further its concept. Let's take another simple 2 input 1 output problem that includes 3 rules. Rule number 1. If x is a3 or y is b1, then z is c1. Rule number 2. If x is a2 and y is b2, then z is c2. Rule number 3. If x is a1, then z is c1. Friends, it may be difficult for you to understand the real meaning of these rules. Therefore, let's apply these rules to a real life problem. Suppose rule number 1 stands for if project funding is adequate or project staff is small, then risk is low. Rule number 2. If project funding is marginal and project staff is large, then risk is normal. Rule number 3. If the project funding is inadequate, then risk is high. Now let's start the fuzzification again. As we know that this is the first step in which crisp input x1 and y1, namely project funding and project staff, are taken and their membership degrees to which these inputs belong to each of the appropriate fuzzy sets are determined. Consider the figure which shows different values for crisp input x1 and y1. Interestingly, they both have 2 fuzzified values at this point. It means that at these values 2 rules are activated. Now second step is rule-based fuzzy inference. In this step, fuzzified input are taken and are applied to the antecedents of the fuzzy rules. As we have already discussed that if a given fuzzy rule has multiple antecedents, the fuzzy operators AND or is used to obtain a single number that represents the result of the antecedent evaluation. When the rule has OR operator, then maximum among the all is taken as below. Whereas when the rule has AND operator, then minimum from the all values is taken as below. Based upon these operators, the aggregated outputs for this case is shown here in this figure. You can see in the first rule OR operator is used, therefore their maximum value is taken. Whereas in the second rule AND operator is used, therefore minimum value is taken. It means that aggregation is the process of unification of outputs of all the rules, in which we take the membership functions of all rule consequents and combine them into a single fuzzy set. The output is one fuzzy set for each output variable. Consider the figure again. Here again 3 outputs are available. Now we have to again obtain the single output by using the defuzzification, which is the last step in the fuzzy inference process. The fuzziness helps us to evaluate the rules, but the final output of a fuzzy system has to be a crisp number. The input for the defuzzification process is the aggregate output fuzzy set and the output is a single number. Friends, it may be noted that mamdani fuzzy inference system always uses center of gravity or centroid method for the defuzzification. Therefore, mathematically the center of gravity can be expressed as below. Applying this centroid on this figure, we will obtain the single defuzzified output as 67.4. At this stage, mamdani fuzzy inference system is successfully covered. Now I am going to discuss the last part of this video, which is based on takagi sugeno fuzzy inference system. As discussed earlier, mamdani method uses the centroid of a two-dimensional shape for the defuzzification. Takagi Sugeno suggested to use a single value as the membership function of the rule consequent and uses weighted average method for the defuzzification. This has a membership function that is unity at a single particular point on the universe of discourse and zero everywhere else. Friends, it may be noted that Sugeno fuzzy inference system is very similar to the mamdani method except in the process of defuzzification. Therefore, let's apply the takagi Sugeno fuzzy inference system to the same previous example. As fuzzification is same as that of the mamdani inference system, therefore we directly start from the second step of the rule base. It can be observed from the figure that takagi Sugeno takes only single values of all the rules rather than considering all the samples as in the case of mamdani fuzzy system. In the next step, all these 3 outputs are aggregated and their defuzzification is carried out by using the weighted average method. The final output by takagi Sugeno method is 65. Friends, it may be noted that in centroid method there were 10 samples and it has the output of 67.4, whereas in the weighted average method there are only 3 samples having the final output of 65. By this way, takagi Sugeno fuzzy inference system works. Now let's compare both the mamdani and takagi Sugeno fuzzy inference system. In terms of accuracy, mamdani system has higher accuracy as compared to the takagi Sugeno system. It is because mamdani takes all the samples and it allows us to describe the expertise in human-like manner. In terms of computational time, mamdani system takes more time as compared to the takagi Sugeno system. Furthermore, it may be noted that mamdani fuzzy system uses center of gravity or centroid method for the defuzzification, whereas takagi Sugeno system uses weighted average method for the defuzzification. Friends, in this video I have basically discussed the basic introduction of the fuzzy logic control. Furthermore, I discussed the mamdani fuzzy inference system and takagi Sugeno fuzzy inference system. In the end, I discussed the comparison between both of them. At the end of this video, we have fully covered the theory of the fuzzy logic control. Now we are in position to start the implementation of fuzzy logic control in MATLAB Simulink. Therefore, kindly stay connected with me. In the next video, I will discuss how to apply fuzzy logic control in MATLAB Simulink. That's all for today's tutorial. If you like it, then don't forget to like my video, subscribe my channel and share this with all your friends so that they may also get benefit from this video. Thank you very much.